Welcome to this module. We are going to take a look at the modulo groups. So let's revisit the modular arithmetic equation one more time, which was introduced by Gauss. It goes like this. So A is congruent to B mod n. So this means A could be written something like this. A is equal to some quotient times B. Quotient times n plus multiplication. This is quotient times n plus b. Okay. But in order to proceed further, we need a much more restrictive definition. This definition is not very restrictive. What do I mean by that? If n is equal to 5, a could be 12 and b could be 7. Right, when we can potentially find a quotient q which works for that. So the much more restricted definition is like this. So A is congruent to R mod n, and we have to restrict this R to be strictly less than n and to be greater than or equal to 0. So if we do this restriction, then we will be able to find an unique q. So here this q is not unique, not unique in the sense like A and B could be any number. For a given A, we can select multiple B's. Okay, so this is Q is also not unique, B is also not unique. If we do this restriction, for a given A, we can only find one R and one Q, which satisfies this equation. Right, so that's the only difference. Now, let's take a look at a simple example, this Z5 set. So, this Z5 set, it has these symbols 0, 1, 2, 3 and 4. For clarity, I'm going to put a little hat on top of these symbols. I'll explain why. Right? So, this denotes a set of all integers which are divisible by 5. Okay, so what are those integers? 0, plus or minus 5, plus or minus 10 and so on. This symbol 4 hat, this denotes a set of all numbers which are divisible, which when divided by 5 gives the remainder 4. Of course, the integer 4 will be there, integer 9, 14 and so on. Okay, but what about the negative numbers? Whether negative 4 belongs to this set 4 hat. Okay, whether negative 4 belongs to this set 4 hat. The answer is no, because negative 4 could be written as negative 1 times 5 plus 1, because we are restricting the remainder to be a positive number which is less than 5. Okay, so the quotient is minus 1. Because of this reason, negative 4 actually belongs to this set 1 cap. So basically this 4 cap is a union of these infinite set 4, 9, 14, 19 and so on, union negative 1, negative 6 and so on. Okay, so you can see that negative 6 is equal to 10 plus negative 10 plus 4. Okay, so that's right. Anyway, so what is a group, right? So in math, an abstract group, let's say a G, the set G will be called as an abstract group with an operator star if it satisfies the following 4 properties. Okay, it means for any x comma y in G, x star y should also be an element of G. Associativity means if we take any 3 elements from G and if we do x star y star z, right, first we operate x and y and then we operate their result with z, or else x star y star z, right? So this should be equal to, first you operate y and z and then you operate on x, then operate the result on x without changing the order. Okay, you might, as a coder, the property, you can exploit these properties to speed up the computations, to speed up to fasten your programs, right? So that's one thing to keep in mind. An identity is an element E which belongs to this set G. When it gets operated on any element X on G, okay, either from the left or from the right, it gives back the same element X. And inverse is for any element X in G, there is an X inverse. This is also another element in G. I'm just giving a different notation, okay? Such that even when you operate it from the right or from the left, it gives you the identity element. Take careful attention. The inverse of the element X inverse is actually X. If X inverse is the inverse of X, then X is the inverse of X inverse, okay? So why these identity and inverse properties are necessary, right? So we are talking about cryptography because to get back, for example, think about the encryption. So you encrypt with a key, so you get a scrambled text, and you need to undo that encryption, which means you need something like an inverse property. Even in digital signature, we don't invert the signature to get the secret key, but this inverse will be used in the operations to actually validate the signature, okay? So we need all these interesting properties to have a working functional cryptography, right? So additive group, okay? Now I'm going to ditch the little hat on these symbols, okay? Because, right, let's understand, it's for brevity, okay? We don't have to keep putting that symbols. So now this additive groups, under the operation addition, it works like this, okay? So 0 plus 1 is equal to 1, or we can say it is congruent to 1 mod 5. If I'm writing equal to right now, it's a shorthand for the congruent symbol, okay? I'm going to ignore that equal to symbol also. Because why not? So 2 plus 3 will be equal to 0. What about 3 plus 4? It's again clockwork, the clock arithmetic that we discussed in the introduction video, right? So 3 plus 4 will be 7. What is 7? 7 is 2 because 5 plus 2. So what about that? What is the identity element of this additive operation? It's obviously 0 because if you add 0 with any other symbols, you'll get the same symbol, okay? What about the inverse? What is the additive inverse of the number 3? It is negative 3, but negative 3, we don't have this negative 3 here. So what should be negative 3? Don't worry, just add 5 to it because 5 is the 0, right? 5 belongs to the 0. Okay, anyway. So 5 minus 3 is 2. So 2 is the negative. 2 is the inverse of 3. What is the inverse of 4? 1, because 4 plus 1 is 5, which is divisible by 5, hence 0, right? And so on. So this is how the additive group thing works. Okay. What about the multiplicative group? So when we talk about multiplication, okay, we know that 1 is the identity element. Okay, so if we multiply 1 with any other number, we get the same 1. So we get the same number back. Okay. But what about 0? Right? Can we include 0 in the multiplicative group? The thing is, we cannot. Okay, I will explain why. The multiplicative group, let's say we need to distinguish it. So let's put another dash above it, okay, to denote that it is a multiplicative group. It does not contain the number 0. Okay, we will soon find out why. Because if you multiply 0 with any other number, you will get 0. You will never get the identity element 1. If we go back to the group definition, every element in X should have an inverse. Okay, so for all X in G, you should be able to find an inverse. Yeah, and for this reason, we don't include, because think about it, if you multiply 5 with any other number, right, any other number, so the result will be a multiple of 5, the result will be divisible by 5. Okay, once again you'll get the 0. Okay, it doesn't matter if it is 15 also. If you multiply 15 with any other integer, you will get a number which is actually divisible by 5. Okay, so for this reason, we don't include 0 in this group. So 2 times 4 is 8, but it is actually equal to 3. We know that, right? And you can do 3 times 4, 12, 2, 3 times 3, what is it? 9, 4. Okay, so now the question is, what is a multiplicative inverse of the symbol 2? I'm keep repeating the term symbol. Okay, I'm not, because we already saw that this 2 is not a number. It is a notation which denotes a set of numbers which when divisible divided by 5 gives the remainder 2. Okay, so what is the inverse of 2? You can say it is 3 because 2 times 3 is 6, which is equal to 1. You get the inverse, you get the identity element, right? So this is the identity element. Identity under multiplication. Yeah, slightly different. So for any number, you should be able to find the inverse. For 3, it is 2 again. For 4, it is 4 times 1, 4, 4 times 2, 8, 3, 4 times 3, 12, but 4 times 4 is 16. 4 times 4 is actually equal to 1. Yeah, let's do the symbolic, extend the symbolic reasoning a little bit, okay? An interesting quiz. Right. So if you consider this set Z6, right, when we are trying to divide with the number 6, we have the 0, 1, 2, 3, 4 and 5. 0 is it represents a set where all the integers are divisible by 6, which are 0, 6, 36, 60 and so on. 2 is all the set of all the integers which gives the remainder 2. Okay, could be the number 2 itself, 8, 14 and so on. You just keep adding 6. Okay, and if you want the negative numbers, you just keep subtracting 6. Minus 4, I mean, and then minus 10, yeah, minus 16, and you can. So that's a trick. Now the question is whether the 0 which belongs to Z5, let's say A is the 0 which belongs to Z5 and B is the 0 which belongs to Z6. Whether A is equal to B. The answer is it does not belong to B. They are not the same. Okay, because this 0, it represents a completely different set of integers, right, which are 5 multiples of 5. And here this 0, it represents a completely different set of integers which are the multiples of 6. I mean, of course they can overlap at some point. For example, take the number 30. Okay, that overlap does not mean that both of the sets are equal. So why this question is important? As a let's say the future SEC P206K1 library contributor or a maintainer, as a maintainer, why this question is important, right? This question is important because in the elliptic curve, if you go and look at the elliptic curve specification, there are 2 primes, P and N. Okay, so the N denotes the order of the like the generator, and this P, it actually uses to compute the elliptic curve points. So when you develop the library, you should know where to take the modulo P and where to take the modulo N. You cannot like interchange them both, right? You need to know that distinction. That's it. Okay, anyway, I hope you understand like at the high level how this modular arithmetic works. In future, we'll just apply this logic to bigger prime numbers. That's it.